to take a few minutes to talk about tests for symmetry. So I want you to take a look at this graph. And now if you'll notice that it looks like a mirror reflection right there through the y-axis. You see the pattern on each side of the y-axis. So this particular graph has y-axis symmetry. Something else I want you to notice about something that has y-axis symmetry. If you'll notice the point here, x equals 1, you'll see it right here, okay? And then you go to the y-axis and you get the point down here, which is what, -6. Also, at x equals -1, you go down and meet the graph and you get the point -6 also. And every graph that has y-axis symmetry has that pattern. So the point 1, -6 is on the graph, and so is the point -1, -6. So in general, what we would say is that if you plug in x, you get the original function. My pen wasn't going to work. If you plug in x, you get the original function. And if you plug in -x, you get the original function, or the original equation, let's say. Okay, so -x and x give you the same equation in the end. Now, I won't do that right now. I just want to talk about symmetry. So this is a graph that has y-axis symmetry, and the point is you get the same value for x and -x. Now let's look at another shape of a graph. Now you see, where would I put the mirror along the axis here? Well, it looks like if I put a mirror right there along the y-axis, the x-axis, right here, we would have a reflection through, right? So this particular graph has x-axis symmetry. Okay, so you would say that this particular graph is symmetric to the x-axis. Now, what's going on with a graph that's symmetric to the x-axis? Well, if we pick a particular x value, in this instance over to the right, x equals 4, you see you get y is +2, and you also get y is -2. So if you keep the x the same, you get two different y values, a +2 and a -2 value. Notice I say for any y value, y and -y have the same x value, okay? So this x gives you +y and this x gives you -y. If we write that down, we could say 1, 2, and 1, -2 are both on the graph. And that has y-axis symmetry. And if I write that in language, we would say, just in general, we would have x, pen issues again, we would have x, y, and x, -y lie on the graph. Now let's look at a third type of symmetry. Notice this particular graph. You notice it's not a reflection through the y-axis, and it's not a reflection through the x-axis either. So it's not your typical symmetry. And maybe what is it symmetric to? It's hard to say. Well, it turns out it has what we call origin symmetry. Now, what defines origin symmetry? Well, let's look at a particular point. If we look at the point on the graph, for instance, you notice there's 5 right here, so that's 1, 2, 3, 4, 5. If I plug in 2, it looks like I get -2. And if I plug in -2, it looks like I get +2 as an answer. So it reverses. So you plug in 2, you get -2, and if you plug in -2, you get +2, and I even have a different point picked out to express that. If you plug in 1, your answer is -4, and if you plug in -1, your answer is +4. And the way you could say that, also notice that for any x, y on the graph, the opposite is also on the graph, and that's what describes origin symmetry. Now, as far as symmetric to, a way to think about that is that if you fold, like this is a piece of paper, and you fold along the y-axis, and then you take that piece of paper again and fold along the x-axis, this part of the graph would land right on top of this part of the graph. Another way is you can rotate quadrant 1, which is top right, over to quadrant 4, which is bottom left, and they would match up, and same thing with saying quadrant 2 could rotate over to quadrant 4. And that's what happens for origin symmetry. And again, I point out this, 1, -4 and -1, 4 are both on the graph. Now we can sum this up all at once. Here we go. So we have the graph of the equation is symmetric with respect to the y-axis. Remember, that's the first one we did. I put that tiny little graph over here for you. If for every point x, y on the graph, negative x, y is also on the graph. That's exactly what we said before. Now, here's how you do it. You substitute negative x for every x in the equation, and when you simplify it, if you get the original equation back, you can say the graph has y-axis symmetry. So you plug in negative x to find out if it has y-axis symmetry. Well, it turns out we do exactly the opposite to determine if a graph has x-axis symmetry. So again, by definition, the graph of the equation is symmetric with respect to the x-axis if for every point x, y on the graph, the point x negative y is on the graph. And that's what we pointed out in our picture. But what do we do to check it? We substitute negative y for every y and simplify, and if we get the original equation back, then we have x-axis symmetry. And I put a graph of the x-axis symmetry we talked about. And then the third one, the graph of the equation is symmetric with respect to the origin if for every point x, y on the graph, then negative x with negative y is on the graph. Here's what you do. You substitute in negative x and negative y, and then you simplify, and if you get the original equation back, then you have origin symmetry. And I put the example of the origin symmetry graph that we looked at earlier. So let's actually do some problems where we determine symmetry. Okay, so here's our first official problem. Notice the directions. Determine whether the graph of the equation is symmetric with respect to the y-axis, the x-axis, the origin, more than one of these, or none of these. Now, what this means is we've got to test all of them. You can't just say, oh, it's y-axis symmetry, and then you're done with it. So there are graphs that can be more than one of these types of symmetry. So we're going to test y-axis first. We're just going to do it in the order that it's written without such a big font here. So y-axis symmetry, remember what you do, you substitute negative x in for x. So I have y equals negative x squared minus 2. And then I simplify that. And when I square negative x, it turns back positive. And notice that matches the original function. It has to match exactly. X squared minus 2 is identical to x squared minus 2. You know what that means? Then our graph definitely has y-axis symmetry. All right, let's try it again. This time we're going to check x-axis symmetry. What do? You substitute in negative y for every y. So I have negative y is equal to x squared minus 2. And there's not really a lot of simplifying we can do there, but you do notice that's not the original equation. I can't simplify this any further. If you like, you can divide everything by negative 1 to make the y positive, but that would make these two guys negative, which is not the original function. Therefore, this does not have x-axis symmetry. And then let's just check for origin symmetry. Now, origin symmetry means you plug in negative x for x, and you plug in negative y for y. You do both. So I've got negative y is equal to negative x all squared minus 2. That gives me negative y on the left, positive x squared minus 2 on the right. That doesn't simplify any further, and it doesn't give us the original function, so this does not have origin symmetry either. So we can say this has y-axis symmetry. Now, so we're used to the idea. I would like to mention a little bit about what y-axis symmetry is also called in function notation, but let me show you the graph. So the graph of y equals x squared minus 2, you see right here, definitely has y-axis symmetry. It's really clear. It's a reflection right down through the line y equals x right in the middle. That's also called an even function, right? If it's a reflection through the y-axis. Our next problem, x equals y squared minus 5. I've got to check these one at a time, so I'm going to check y-axis symmetry first. So does my graph have y-axis symmetry? Well, I've substituted in negative x for x. So I have x is equal to, oh my bad, I didn't plug in negative x for x, did I? Let's try that again. So negative x is equal to y squared minus 5. Now, you could simplify this further by dividing everything by negative 1. You will see you won't get the original equation back, and this is not the original equation either, and there's really no simplifying to do. So this particular graph does not have y-axis symmetry. Now we move on to x-axis symmetry. The rule is here you substitute in negative y for every y. So x equals negative y all squared minus 5. I reduce, that gives me x equals y squared minus 5. Notice that matches the original function. So we can say that our graph has x-axis symmetry. But we've got to check for the third one as well. So I'm going to substitute in negative x for x and negative y for y, and this is called origin symmetry. So I have negative x is equal to negative y all squared minus 5. That gives me negative x is equal to y squared minus 5. That is completely simplified. It is not identical to the original function. Therefore, this graph does not have origin symmetry. It only has x-axis symmetry. Now, when you look at the graph, you will see this definitely has x-axis symmetry. I can draw a line right through the x-axis here, and you see it's a reflection on both sides. Now, if you think about it, this particular graph does not define a function. You remember why this doesn't define a function? Well, because it fails the vertical line test, right? If I draw a vertical line right here, it intersects the graph more than one time, so it's not a function. So any graph that is symmetric about the x-axis is going to fail the vertical line test, in general anyway. Therefore, this is not a function. So we won't be talking about this in terms of functions, anything that has x-axis symmetry. But again, y-axis symmetry does define a function, and we have a special name for that, and those are called even functions. So let's go on to another problem. So example C, y squared equals x squared minus 4. Go ahead and pause it, and you check all of these yourself. Okay, so let's first check y-axis symmetry. And when you check y-axis symmetry, you're plugging in negative x for every x. So that's y squared is equal to negative x all squared, subtract 4. When I simplify, that gives me y squared equals x squared minus 4. Remember, when you square a negative, it turns positive. This matches the original function. Now, what does that mean? That means we do have y-axis symmetry. Now, let's check our next one. Do we have x-axis symmetry? What is the rule? You substitute in negative y for y, and then simplify. So I'm going to have negative y all squared equals x squared minus 4. Negative y all squared is y squared equals x squared minus 4. Okay? And then does that match the original function? Sure it does. This is the first one we've run into that we have both y-axis and x-axis symmetry. And then finally, we check both of them. Now, you may already have an opinion about this. This is called origin symmetry. Okay, so we're going to plug in negative x for x, negative y for y, and that's going to give me negative y squared equals negative x squared minus 4. When I simplify that, that gives me y squared equals x squared minus 4. Notice that matches the original also. Now, what do you think? If a graph has y-axis and x-axis symmetry, would it naturally have origin symmetry also? That's something to think about. Let's look at the graph. There we go. So notice it definitely has y-axis symmetry if we reflect through and not move the graph. If we reflect through the y-axis, we could mirror over and we definitely have symmetry. What about x-axis symmetry? Well, there's my x-axis right there. If I fold right along the x-axis, we get the same graph. And what about origin symmetry? Remember, if you rotate the first quadrant, over to the third quadrant and the second quadrant, you rotate over to the fourth quadrant, would it match up? It would. You can also picture folding down the y-axis and then again folding over the x-axis to make a quarter of a sheet of paper, and then all these lines would land on top of each other. So that's going to give you origin symmetry. So this definitely has all three. What else? It's not a function, right? Because if you draw a vertical line, say just for example right here, it intersects more than one time, therefore this graph does not define a function. So next problem, determine whether the graph of the equation is symmetric with respect to the y-axis, the x-axis, the origin, more than one of these or none of these. Let's keep going. So to check x-axis, you know the drill. To check x-axis, I'm going to substitute in negative y for y. Alright, so that's going to give me x to the third minus negative, I don't know why I'm doing x-axis first, but we're going to go with it, negative y squared equals 5. So that gives me x to the third minus y squared equals 5. Notice that matches the original. So what can I say? We do have x-axis symmetry. Let's keep going. And really what I wanted to check first was the y-axis symmetry. So y-axis symmetry, you plug in negative x for every x. That'll give me negative x to the third minus y squared equals 5. And then when I simplify negative to the third power, it remains negative. So negative x to the third minus y squared equals 5. Notice that does not match the original. Negative x to the third certainly is not the same as positive x to the third. The minus y squared matches and the 5 matches, but everything's got to match. Therefore, this does not have y-axis symmetry. And then origin symmetry, I'm going to put over here on the right. And you have negative x and negative y. We're going to substitute in both. So if I have negative x to the third minus negative y squared, does that equal 5? Well, we're going to simplify it. It's going to equal 5 no matter what, but does this match the original? Negative x to the third, when you raise a negative to an odd exponent, you're going to get a negative overall. Minus y squared, negative y all squared is positive y squared. So it's going to be negative y squared equals 5. Now when I simplify this, so again, notice the negative went away. This negative simply came down. This negative y squared turns into positive y squared. This does not match the original function, you'll notice. So this does not have origin symmetry. So the only thing we can say is that it has x-axis symmetry. Let's take a look at the graph and see if that matches up. And there we go. There's the graph. Does this have x-axis symmetry? Well, I can draw a line right there along the x-axis. If I fold, I definitely get this line will land right on top of this line. So our test was correct. Now let's keep going. Next example. X squared plus y squared equals 81. So I'm going to keep it in the same order this time. Does this have y-axis symmetry? What do? We plug in negative x. So to remember this is the opposite value that you're plugging in negative. So you have x, negative x squared plus y squared equals 81. Simplified, that gives me x squared plus y squared equals 81. Notice that is the original function. Therefore, we do have y-axis symmetry. All right, let's check for x-axis symmetry. I'm going to plug in negative y for y. It's going to give me x squared, parentheses not required, plus negative y squared equals 81. This is x squared plus, what happens to this negative? It goes away because we're raising it to an even power, plus y squared equals 81. Look, I got the original function again. Again, if it has both x-axis and y-axis symmetry, we're thinking just maybe it might have origin symmetry as well. But we can always check it, right? So origin symmetry, if negative x and negative y produce the original function that we're started with, how about negative x all squared plus negative y all squared equals 81? Well, sure, right? Negative x squared is x squared. Negative y squared is y squared equals 81. That definitely matches the original function. So we do have origin symmetry. So what's that going to look like? So the graph of x squared plus y squared equals 81 is to the right. And if you'll notice, that is a reflection through the y-axis, right along here. That's when we plugged in negative x for x. It's a reflection through the x-axis along here, and that's when we plugged in negative y for every y. And if we rotate what's in the first quadrant over, it's going to land on top of what's in the third quadrant. And you would also have to rotate what's in the second quadrant, and it'll land on top of what's in the fourth quadrant. And you have a circle here. It's actually a circle with radius 9. And coming up not too long, we will be talking about the equation of a circle and how you would come up with this particular circle. Now I'd like to extend the same conversation we had about y-axis symmetry, origin symmetry, and x-axis symmetry to functions. And so what you have here is an equation, y equals x squared minus 5. It has a graph that is symmetric with respect to the y-axis, because if you plug in negative x for x, you will get the original function back. That's also called an even function. We mentioned that earlier. Matter of fact, this particular graph, y equals x squared minus 5, is a parabola shifted down 5 units. And it is symmetric through the y-axis. It's even. Now, the thing is, when you have an equation that passes the vertical line test, it can be written in function form. So you'll notice this is, of course, in function form, and it's the same equation we have here in just equation form. So when you write it in function form, you could say it has symmetry around the y-axis, or you can call it an even function. Now, what is the test? What do? Is you substitute in negative x for every x, just like you do to check for y-axis symmetry. When that simplifies, if you get the original function back, then you have an even function, which is the same as saying you have y-axis symmetry. So for our next equation, let's take a look at y equals x to the third minus 2x. Now it turns out this particular equation has origin symmetry. How do you check for origin symmetry? Remember, you substitute in negative x for x and negative y for y. And let's do that real quick just to check it. So you'd have negative y is equal to negative x to the third minus 2 times negative x. I simplify, that gives me negative y equals, now negative x to the third is negative x to the third without parentheses. And negative 2 times negative x is plus 2x. Now right now that does not look like the original function. But if I divide everything by negative 1, that would give me y is equal to positive x to the third minus 2x. Notice that matches the original function. Well, it turns out this particular equation, because it's solved for y, and remember there's no plus or minus over here, can also be written in function form. Now, there's a slightly different rule when it's in function form, but I can tell you origin symmetry is the same as calling a graph odd. And think odd origin, okay? So odd is the same as origin symmetry. Now the test for whether a function is odd is you plug in negative x for x, just like if it's even. But when you plug in negative for x, if you get exactly the opposite signs, like in this case, then it is a odd function and it has origin symmetry. So notice that they do mean the same thing, but the tests are different. The test, when it's in equation form, you plug in negative x for x and negative y for y and see if you get the original function back. But when it's in function form, you plug in negative x for x and see if you get opposite the original function, which essentially is just saying you get negative y on the other side. All right, let's keep going. Now, for these problems, we're just supposed to flat out determine whether the function's even, odd, or neither. And the test is really to substitute in negative x for x. So it's not like 3 different tests when we were looking for x-axis, y-axis, or origin symmetry. When it's in function form and you're just testing for even, odd, or neither, just plug in negative x. You simplify your expression and then check to see if you get the original function back or if you get opposite the original function. Now when I take a negative and raise it to the 4th power, it turns positive. Now it doesn't change this sign, that just comes down. The negative x to the 4th is x to the 4th. Now this negative x squared turns positive. And look, I've got the original function. Notice that that matches the original. Therefore, we have even symmetry. Now you can't be both even and odd. That is impossible when you have a function. Okay, so here we go again. Is this function even? Is it odd? Or is it neither one of those situations? So if we have g of x equals negative x to the third plus 3x, what am I supposed to do? I'm supposed to plug in negative x for x. So it's going to be g of negative x is equal to negative, and then that's negative x to the third plus 3 times negative x. Now, negative x to the third is negative x to the third, so it's going to be negative times negative x to the third. Why did I keep the parentheses? Because I haven't multiplied these two negatives together yet. This is going to be minus 3x. Well, that's going to give me positive x to the third minus 3x. Now look at your signs. Notice the negative x to the third is now positive, and the plus 3x is now minus 3x. That is the opposite of your original function. Therefore, this is an odd function. Has to be opposite all the way, not just part of the way. It also means it has origin symmetry. And then our last example, let's take a look, same question, but a different function. Determine whether the function is even, odd, or neither. And if you see these directions, that means plug in negative x for x. So I'm going to find h of negative x. That's going to be negative x to the third plus 3 times negative x minus 5. Now this function ought to look a little bit familiar. If it didn't before, it will now. When we simplify just this, the negative comes down. Negative x to the third power is negative x times negative x times negative x, which is overall negative x to the third. Now positive 3 times negative x is minus 3x minus 5. Now this negative, think about it as a negative 1 times negative x to the third is positive x to the third minus 3x minus 5. Now compare this to your original function right here, and notice the negative x to the third turned positive, the positive 3x turned negative, the negative 5 did not change. And since that last one does not change, this is a neither situation. X to the third minus 3x minus 5 is neither even or odd. Which also means it doesn't have a y-axis symmetry, and it doesn't have origin symmetry. And that's the end of my symmetry examples. I hope you have a wonderful day. Let me know if you have any questions, right?